we have been using logic-based methods to explain machine learning models. So, and what I'm going to do is give you a brief overview of the work we have done. So everybody is familiar with the successes of machine learning, and this explains the interest in reasoning about machine learning models. We have self-driving cars, we have the different contributions of DeepMind, we have personal digital assistants, robotics, we have image and speech recognition beyond what human can do, and so on. What is explainable AI? Very quickly, it's very simple. So most of the successes that I've just briefly mentioned use black box models, and for example, neural networks. And these are called, their operation is opaque. We humans don't understand what is going on with these neural networks. So the goal of explainable AI is to help humans understand machine learning models. And of course, this raises several questions. What does it mean to be an explanation to be understandable for a human decision maker? How to answer a why question? So why this prediction, or to answer a why not question, which is sometimes interesting, why not some other prediction? For example, if a bank loan is rejected, why not? What would I have to do different to get the bank loan? Do I have guarantees of rigor? And there are other questions just besides computing one explanation. I might be interested in navigating explanations because different humans relate with different types of information, deciding whether some sensitive feature is included in some explanation and so on. Okay, and what we have also noticed is that there are important links between expandability and robustness, fairness, and even learning of machine learning models. For those of you less familiar with the area, there is a vast interest of expandability. At least, for example, in Europe, there is the GDPR since 2016, and some people would argue that GDPR entitles you to explanations made automatically by algorithms. There has been an effort by DARPA on explainable AI, and there is the more recent proposal for guidelines on AI in Europe, which also address explainability. What we've been doing, completely my team at Unity, is focusing on high risk and safety critical applications. So high risk, according to EU regulations, for example, if you use AI systems in law enforcement, managing or operating critical infrastructure, categorization of people, and so on. Safety critical are standard ones like self-driving cars, autonomous vehicles, and so on. What the EU has done is to categorize possible uses of AI according to a pyramid, and you have uses that are offer an acceptable risk, and in those cases you cannot have AI uses. And then you can have a minimal or limited risk, and these ones are not sensitive. And then you have applications where the uses of AI are high risk, and these are the ones we are interested in, and these are the ones I mentioned, some of which I mentioned here. The importance of being able to explain what is going on is so important that some authors, in this case this author here, even proposed, and again this is just one of many authors that proposed not using black box models and using instead interpretable models, meaning models that humans can understand what is going on when we are talking about high risk or safety critical systems. And so in these cases, high risk and safety critical, the correctness of explanations is paramount. So for several reasons, to build trust, to prevent accidents, disasters. It's much easier. Risk and safety critical applications are the main motivation for our work. So this is the outline of the talk. I'll try to define the setting we are working on, and then explain why what people have been doing, most of what has been done in the past is problematic. Summarize the progress that we have registered in formal explainability, and talk a little bit beyond just computing explanations. So we are going to talk about classification problems. In a classification problem, you have a set of features, and each feature takes values from some domain. And the domain can be categorical, or it can be discrete valued or real value. And by having the features with their domains, we can define feature space, which is just the Cartesian product of the domains of the features. And because we have a classification problem, we also have a set of classes. And the machine learning model computes some classification function. For simplicity, we assume it's non-constant, otherwise it would not be interesting. A classification function that maps any point in feature space to one of the classes. And concretely, when we are talking about explanations, we consider one instance, which is a point in feature space, and its associated prediction. So C is the value associated by the classification function to the point V in feature space. Okay. So let me talk a little bit about the limitations of non-formal explainability. So if you search the bibliography, 99.9% of the papers that you're going to find, or even more than that, talk about two main approaches, or essentially one main approach. So it is what is called model agnostic explainers, and perhaps the most famous are Lime and Sharp, but also Anchor is quite well known. So in Lime and Sharp, the idea is that you learn a simple interpretable model, for example, a linear classifier, or for example, a decision tree, and then what you do is you train the classifier with different approaches locally, so that you have what is supposed to be locally rigorous explanations. Anchor operates in a similar way, but with different goals. So the goal in Anchor is that you learn the features that are relevant for the prediction. So you don't care about some other simpler model, you care about the features that are relevant for the prediction. Like Lime, Anchor is sample-based. So you sample the feature space, and with this, you deem which features are important. Now, I should note that none of these approaches have offered formal guarantees of rigor in the computed explanations, and I'm going to talk a little bit about that. An alternative is intrinsic interpretability. So the model is itself the explanation. And as I said, some authors propose this. One example is instead of using a neural network, you are going to use a decision tree or a decision list or a decision set. Of course, it's not the same thing, but this is what some authors propose to do. Now, the question we asked a couple of years ago is, can we trust model agnostic explainers? Do we have interpretability when we are talking about intrinsic interpretability? And so let me give you a first example. So this example, we first came across it in 2019, so almost 3 years ago. So this is a classification problem, a very well-known data set, a zoo data set. We created a very simple boosted tree. So these are a boosted tree is a bunch of trees. So each of these boxes is a tree. So we have 7 trees, one for each class. As I said, it's a very simple example, and each tree tests just one feature. And so we plug in values to the features, and then we, even the one that maximizes the output, we predict the class. So for example, we can check that if we have this instance, animal is pit viper, not hare, not feathers, and so on, then the class should be reptile. So for example, this means that this is the tree that outputs the highest value, so it should output this value compared to the other ones. Okay, so the question is, okay, what is an explanation for this prediction? And if you run Anchor, well, Anchor is randomized, so this is one of the possible runs. You run Anchor, and it says not hair, not milk, not tooth, and not fins. So an interpretation would be that as long as you have not hair, not milk, not tooth, and not fins, you should predict reptile. So this is the rule that we see as the explanation. Okay, what is the problem? The problem is that this same explanation explains another instance with a different prediction. So we went through training data, and we came across another instance where the class is no longer reptile, it is amphibian, and the explanation is consistent. So this is what we see as a huge problem for these methods. So what am I trying to say? Let me put it in a different light. So suppose you have a classifier for deciding bank loans. So, and you have 2 samples. You have Bessie, which has some features, and the bank loan was approved. And you have Clive, which has some other features, and the bank loan was declined. And then you have an explanation, X, say age is 45 and the salary is 50K. And what happens is that X, your explanation, is consistent with Bessie, so for the approved loan, and X is also consistent with Clive for the declined loan. So the point is that you have different outcomes and you can get the same explanation. So the explanation doesn't mean anything. And this is what we observed in this model agnostic explainers. Now you could say, well, how serious is this? And the answer is that we got a few years ago is that it's very serious. So we ran Lime and Anchor and Sharp, and we could have incorrect, redundant, or correct explanations. And we observed that for some data sets, you can get 99.9, 99.7, 94.1 incorrect explanations. So again, this shows essentially that most of the, or almost all of the explanations that you are computing are incorrect. Okay. Now this is here. The exercise was: can we prove the explanation correct? Another way to look at it is how incorrect is the explanation. So it could be just one point that is destroying the explanation. And what we observed is that that is actually not the case. For some, this anchors means examples. For some examples, the precision, so you can get explanations that are 50% correct. Most of the 50% of the time they will be incorrect anyway. Okay, so this is, as I said, we think this is extremely serious, and we have been reporting this for 3 years now. So a different alternative, as I mentioned from the beginning of the talk, was to use interpretable models. So, and of course, what is the, if I ask any of you, what is an example of an interpretable machine learning model, I would assume everyone would say decision trees. So for more than 20 years, people agree with this statement on interpretability: trees rate an A star. Okay, so are decision trees interpretable? So this is an example from this paper. So it's a fairly recent paper, and this paper proposed to compute optimal sparse decision trees, OSDT, optimal sparse decision trees. And so this decision tree was computed with this tool, and this is presented in this paper. And so let me talk about the concrete path in this tree. So suppose that we have this path here. So to simplify the notation, instead of using middle, top, left, and so on, I just use MM, TL, and so on. Okay. And so the explanation, according to what people proposing to use intrinsic interpretability, they would say, well, this is the path is the explanation. So the explanation is if I have MM0, TL0, BR1, BL0, and TR1, then the prediction is 1. Okay, so this looks fine. It's not a huge explanation. It looks fine. Can we do better than this? And essentially, so this is the path, as I just said. If we construct a truth table and try the possible values for MM, all the possible values for MM, BL, and TL, TL here, sorry, this one, you see that the prediction never changes. So this means that we can go from the path to an explanation with 2 literals, and we can drop 3 literals. Okay, so this means that we can have redundancy in the path of decision trees in terms of explanations, and we should get rid of them. Of course, for a human decision maker, 2 literals is much easier to explain and reason about than 5 literals, of which 3 really don't mean anything. Okay, so you could say, oh, that's just one example, and it's not really the case. So here in this tree, I have 8 paths, and 5 are redundant. And again, as I said, this tree was supposed already to be optimal sparse intended for interpretability, which is not the case. So actually, we proved something stronger. We proved that interpretability can be arbitrarily large. Sorry, redundancy can be arbitrarily large. So let me just very quickly explain what is the idea. So suppose you have this classifier. So it just computes the disjunction of the input features, which are Boolean. And one possible decision tree is as follows. You pick the order, it doesn't matter. So you pick Y1 and Y. This is the index. So the first the first feature is going to be taken from the index I1, index I2, and so on. So you test index I1. If the feature is 1, of course, the output is 1. Otherwise, you don't know, and you continue. You try I2, and so on until the end. Okay? So, and now suppose I ask you the following. Suppose I have this point where, so I respect that order, which can be any order. So I'm not imposing the order. The only thing I'm going to do is use that order, and everything is 0 but the last one. Okay, or clearly because it's a disjunction, this is going, the prediction is 1. So I should end up here. Okay. Now, what is the explanation? We could say, well, if it's the path, then it's because this one, sorry, this one is 0, this one is 0, and so on, and then this one is 1. So if this is 0, this is 0, and so on, this is 0, and this is 1, then the prediction is 1. Okay. What happens is that it's clear that as long as the last one is 1, the feature IM is 1, then the prediction is going to be 1. So I can write that for any point in feature space, if the XIM, so the feature IM is 1, then the output is 1. So this is my explanation. So the point is that the actual explanation can be arbitrarily smaller than the path in a decision tree. So the path here grows with the number of features, and the explanation size is 1. So what we conclude is that decision trees are actually not interpretable as long as you associate interpretability with anything that relates with succinctness of explanation. Okay. So let me now talk about what we propose. So what we did is take a different approach to explainability, and what we did is propose a formal grounding for explainability. So again, as I said at the beginning, we have an instance, a point in feature space V and its prediction C. And we propose 2 types of explanations. So something what people, and it's not just us, other groups are doing the same. So we call them abductive explanation or PI explanation. So this is the answer to a why question, why the prediction. So an abductive explanation is a subset minimal set of features. So you pick a subset of the features, which is sufficient for ensuring that you predict the class that you are interested in this case C. So how do we represent this in logic? So for any point in feature space, if the features in the set are fixed, so if they don't change value, then the prediction is what we want. Okay, so this is how we define abductive explanation. We can talk about, and as I said, sometimes it's interesting to talk about why not some other prediction. So we call that a contrastive explanation. And it answers, as I said, the why not question. And again, as before, we define it as a subset minimal set of features. So a subset of the features that if we allow these features to change, then we can change the prediction. So what we are saying is that now there exists some point in feature space such that for the features that are not in this set, if we fix them, so the ones in this set, we allow them to change, then the prediction can take a different value. Okay. And again, to be subset minimal, if given this predicate, what we need to do is that this predicate has to hold, and for any proper subset, the predicate must not hold. So what we are saying is that if we define this as being a weak AXP, a subset minimal AXP or CXP is essentially asking for a set that is a weak AXP, and any proper subset is not a weak AXP. What we also proved, and it's interesting, we think, is that abductive explanations are minimally thin sets of contrastive explanations and vice versa. So this essentially allows us to use abductive explanations to compute contrastive explanations and vice versa. So another observation, and again, I'm not going to prove this result, just make the claim, is that the conditions for weak abductive explanations and contrastive explanations are monotone. And this means that instead of trying all the possible sets, and that would be extremely difficult to do in practice, we can just take one element, check all the elements in the set and take it out and make sure that the predicate is no longer true. So this means that we can simplify the definition of abductive explanation. So it has to be a weak set is an abductive explanation if it is a weak abductive explanation, and for any feature, if I drop the feature, it's no longer a weak explanation. So how do we now compute explanations? Well, we have to encode the classifier in some suitable logic representation. And then for either objective explanations or contrastive explanations, we can start from the set of features and then drop features while it's still a weak objective or contrastive explanation. So, of course, the question is which reasons to use, and I'm going to talk about this shortly. So, just to simplify so essentially we say that we have a set is an objective explanation if this condition holds, so it's not consistent this logic expression. So essentially what I have to do is encode this in some logic representation and then use a reason for this, for the theory. Okay, and I can do this for objective or contrastive. For objective, I don't want consistency. For objective, I want consistency. The expression is exactly the same. Okay, and so this is leads to, for subset minimality, I can have very simple algorithms. Of course, the challenge is the encoding, which is hidden here and hidden here. Okay, so let me show you how this can be done with a very simple example, and then hand and wave and show how we can do this for more complex examples. So let's look at this again. This is a classifier that is a disjunction of 4 features, Boolean features, and we have a point in feature space with, of course, prediction 1, and we would like to compute an objective explanation for this point in feature space. Okay, so how do we do this? So first we start with all the features 1, 2, 3, 4. So 1, 2, 3, 4, and what we do next is we would like to remove the features if possible. So let's use the order 1, 2, 3, 4, but the order could be any. Okay. So the question that we ask is, can feature 1 be removed? So how do we remove feature 1? Essentially, what we are going to do is we are going to allow feature 1 to take any value. So we are going to pick any point in feature space. Feature 1 is not constrained, but feature 2, feature 3, and feature 4 must be 0, 0, and 1, as it's shown here. And this must imply that the prediction must be true. Okay, it's easy to see that that is the case. Why? Because as long as x4 is 1, because it's a disjunction, if x4 is 1, then this is going to be 1. So yes, I can drop feature 1. And I can continue asking the same question, similar questions for other features. So can I drop feature 2? Now, I'm asking this question given that I already dropped feature 1. So to drop feature 2, I'm going just to keep fixing feature 3 and feature 4. And I want to know if the prediction is still implied. And as I said before, because it does not really depend on x1, x2, and x3, the answer is yes. So I don't need x2. They can ask the same question for feature 3, and again, the answer is going to be yes. And finally, I can ask the same question for 4, given that I already removed 1, 2, and 3. So essentially, is it the case that the prediction is always 1? And the answer is, of course, not, because if I change 4, I can change the prediction. So the answer is no. So this means that my objective explanation, so for this classifier, for this point in feature space with this prediction, as long as feature 4 keeps its value, the prediction is going to be true, which makes sense. Okay. Now this I did by hand, with asking questions and trying to be convincing. But of course, this should be done automatically with reasoners like a SAT solver or an SMT solver, a mixed integer linear programming package, and so on. Okay. Now this same analysis we could do. I forgot to mention that. So I'm going to mention this for some classes of classifiers. We don't even need this. We can do it in polynomial time, and I'm going to mention this very shortly. For contrastive explanations, it's the same rationale. I'm going to speed just to say it's the same, exactly the same approach. The only thing that the difference is that when I say removing, essentially I'm having features because we are working with a complement in the definition. So as you can see here, but it's exactly the same procedure. Okay. Now, until now I've not given you the details. So everybody should be asking, okay, this is fine. How do I do, for example, a neural network? So let's talk about neural networks. So this is an example of a neural network with three layers, but we don't count the first one because we are not going to look at the first, just the other layers. And each neuron has an activation function, which is the Relu activation function. So if I'm assuming everyone is familiar, because it's very simple. So if the input is less than or equal to 0, the output is 0. Otherwise, it tracks the output tracks the input. Okay, and so as I said, ignoring the first block, each block here can be viewed as divided into two parts. We compute an intermediate value x prime given the input x and some weight matrix and the bias vector. And then given x prime, we compute the output using x prime and an activation function, which we are going to use Relu. Okay. So what we need to do now is what I showed in the previous slide is this. So we compute an intermediate value x prime, which is the dot product between the weight matrix and the input, and then the bias vector, summing the bias vector. And then I compute the max between 0 and x prime. Now the question is, how do we represent this in some suitable representation, for example, mixed integer linear programming or satisfiability model theories? So we picked an encoding, a fairly recent encoding. So notice that this the matrix product is shown here with the summation shown here. So we just do the summation and we add the bias vector. And now what can happen here? Well, it can be positive or negative. So if it is positive, yi is going to take the value, which is the output. If it's negative, si is going to take the complement of that value, where yi and si are both positive. And how do I pick? Well, I have to pick one of these. So I'm going to use a Boolean variable, which essentially only allows one of these two variables to be non-zero. So if zi is 1, then yi is less than or equal to 0 and greater than or equal to 0, so it's 0. And if zi is 0, then si is less than or equal to 0 and greater than or equal to 0, so it's 0. Okay, so we can view the si as a slack variable that keeps negative value, the complement of negative values when the summation is negative. Okay, so just to show you an example of this encoding, so for a very simple neural network, just one neuron essentially. And here the summation is x1, x2, as you can see from the weights, minus 0.5. And then here you have use the trick of the two variables, y1 minus s1. And then we use a Boolean variable to say one of these is non-zero and the other must be 0. And then we compute the output. This is just an OR function. So we compute the output as shown here. Okay, so this is the encoding from the previous slide, and what we can do is we can feed this to a mixed integer linear programming package. Here I have two examples of plugging in values just to show how it works. Okay, so what I just did is to show you how we can use the theory that we have been talking about to reason and explain, for example, neural networks. Just some results that we got in 2019. So these are data sets, the minimal subset minimal explanation, subset minimum of smallest explanation. We tried SMT solvers and mixed integer linear programming solvers as well. Number of features, smallest, largest, and average size of an explanation, and a few more data points. So I did not mention this, but computing a smallest is computationally harder than computing a subset minimal, and this is shown reflected here. So in some cases, you cannot compute. And well, the explanation size can go from very small to pretty large compared to the number of features. So the claim is that this was the first rigorous approach for explaining neural networks 3 years ago. The downside is that we can do this with a few tens of neurons. So again, of course, people are interested in neural networks with millions of neurons, and we can do 40, 50 neurons. So that was not really the most positive result. But again, don't get desperate. We have some positive news, of course. As I said at the beginning, in terms of decision trees, they can have redundancy. We need to explain them. And computing explanations, in this case, it's easy. So one way would be to use the algorithm I outlined before, and this would be worst case exponential time, but we don't have to do this. So suppose in this case, in this complete case, the prediction is 1. So notice that I don't care about the values of features as long as I'm not allowing any path to 0 to be consistent. So essentially, I need I can drop features, I can make features irrelevant as long as I'm not allowing one of the paths to 0 to become consistent. So essentially what I have to do is find a subset minimal eating set of all these 0 paths. So these are the features that I need to keep. And this, well, it's well known to be solvable in polynomial time. So in this case, for example, if I fix this feature, and if I fix this feature, then I can prove that, notice that this value is irrelevant because it's 1. And here the value is relevant because I'm fixing it, it's going to be 1. So this one is not relevant. And this one also not relevant. And this one also not relevant. So this means, as I said, showed at the beginning of the talk, I just need 2 features to explain this prediction. Okay. Now, here we implemented, again, this runs in polynomial time. So the run times are very small. Now, what is interesting is that you could say, well, but do we see this a lot in practice? And the answer is yes, we see the importance of removing redundancy in explanations of decision trees in practice. So these are 2 different tools on different data sets. IAI is a company in the US, Interpretable AI. So they create decision trees that are interpretable. And what we showed is that the decision trees they create so they can have, for example, here, 86% of the paths are redundant. 80%, 80%, 60%, and so on. And so this means that most of the paths that you have in the, well, most 80%, 86% of the paths that you have in the decision tree are redundant, and that the percentage of literals that are redundant in the path can also be significant. Okay, so as I said, this is a tool that exists to produce interpretable decision trees, and what we showed is that, well, you should explain the decision tree because you're going to get significant amount of redundancy in the paths that you are going to look at. And this is an older tool, and the same picture can be observed. So we have a lot of redundant paths in decision trees, and a significant percentage of redundant literals in paths that are redundant. Okay. So let me give you a glimpse of what we have done besides devising the framework. We also obtained some results that are important in terms of what we can compute efficiently. So over the last 2 years, what we did is looked at formal explanations for different families of classifiers, and we proved that in several cases, computing one explanation is in polynomial time. So concrete examples. If you have a naive-based classifier, well, you can compute one explanation in polynomial time. As I showed before a few slides back, for decision trees, that is also the case. So you can compute one explanation in polynomial time. If you have a monotonic classifier, and this can be any classifier, so suppose you have a neural network, as long as you know it's monotonic, then we can compute one explanation in polynomial time. If you use propositional languages as classifiers, you can explain them in polynomial time. If you use the different types of decision tables and graphs, you can compute them in polynomial time. So this is shown here in green. So it is practically very effective, and it runs in polynomial time. We also proved that in some cases, computing explanations is computationally hard. So that is the case with random forest, cluster trees, and decision lists. Now, this is might not seem positive, and it's not, but in practice, we show that there are logic encodings which allow us to compute explanations very efficiently in these cases. And I'm going to mention that in the next slide. And finally, there are well, these were the good news. The less good news or negative news is that for Bayesian networks and for neural networks, we still are not able to compute explanations efficiently. Okay, just to give you a glimpse. So this is results for random forest from last year, and some data sets. And again, there is a lot of information. I just want to highlight some important aspects. So notice that here we are computing explanations. So this is the tool that we developed. This is the average runtime of our tool. This is the average runtime of Anchor. So as you can see, we are computing rigorous explanations. Here we are calling a SAT oracle several times, and still we are much faster than Anchor. So the bottom line is that, as I said in the previous slide, computing explanations for random forest is computationally hard, but in practice we can compute them very efficiently. So this is the average time to compute one explanation. Okay. Okay, so what have we done besides computing explanations? So we have looked at a few more problems. So one is enumeration. So we want to list explanations because a human decision maker might not be happy with the explanation that is given. And so so first we have exploited duality to compute to enumerate explanations, number one. And for naive-Bayes classifiers, we prove that you can enumerate explanations with polynomial delay. So this was a result of 2 years ago. We have also investigated membership. So there's some sensitive feature, like for example, gender, can it be used to make a decision on a bank loan, for example? And so this relates with fairness, for example. And we prove that for DNF classifiers, deciding membership is sigma to P hard. But what we also prove that for decision trees, it's in P. And if finding one explanation is in P, then it's in NP to decide membership. So that's also an interesting recent result. Finally, because the size of explanations can be large, we have been looking at probabilistic, we and some other people have been looking at probabilistic explanations. So the idea is that instead of having absolute rigor, we are trading off rigor for smaller explanation size. And there is a result, an avoidable result, that for Boolean circuit classifiers, computing probabilistic explanations is NP to the PP hard, so it's extremely hard to solve in practice. We have better results in some concrete cases. And yes, we can look at the same problems in a more general setting instead of looking at a concrete instance. So to summarize the talk, I gave you, I started by talking about the very important limitations of XAI approaches that people are using. So I try to convince you that model agnostic methods, and this applies also to saliency-based methods in for neural networks, they can compute incorrect explanations. So if rigor is important, that's problematic. And if you instead prefer to use intrinsic interpretability, so to use an interpretable model, the explanations we showed can be very redundant. I introduced formal expandability. So we have logic-based rigorous definition of explanations with some initial theoretical insights. And we also talked about some problems like listing explanations and deciding membership of features in explanations. And I also briefly mentioned the research that we are looking at. So one is, of course, more efficient methods for example, neural networks or Bayesian networks, which we don't have a good answer yet. How to be efficient in terms of enumerating explanations, and also efficient methods to decide membership. And finally, how can we compute probabilistic rigorous explanations? So this is open research right now. Thank you very much.
Thank you. Other questions?
Hello, can you hear me?
Yes.
Okay. Is there a, I didn't quite get, is there a complexity gap between the minimum and between computing the minimum, a minimum
Yes.
set and the minimal set in general and in some classes of
That is a very good question. There is in general, not always, but in most general cases, there will be a gap between computing a subset minimal and computing a cardinality minimal explanation. So this relates with computing prime implicants of Boolean functions, and there you have the same situation. So what the results that we have is that computing a subset minimal so you can solve it with a logarithmic number of calls. Sorry, a linear number of calls to an NP oracle, whereas computing the smallest is a sigma to p hard, smallest explanation. So of course, this depends a lot on the complexity of reasoning about the model itself, and that's why I'm hesitating a little bit. So the complexity that I'm mentioning is for most reasonable machine learning models. So for example, for a neural network. But if you are talking about a Bayesian network, you get the different complexity results. So, but for a neural network, that is correct. So, computing a subset minimal, you need to call an NP oracle a linear number of times in the worst case, and to find the smallest, it's hard for sigma to p. So, you may need to call an NP oracle an exponentially large number of times.
Thank you.
Hello, can you hear me? I
Yes.
have a question, maybe about the monotonicity, and maybe two questions. I'm not sure I understand the things correctly. First of all, what's happening in the situation? Is it a relevant situation when I don't have necessarily all the values or the features, and on the basis of the values I have, I make a prediction, but then if I get more values, this prediction can be overridden. Is it significant, this situation? Is it kind of non-monotonic prediction?
So again, I mentioned monotonic with two different. So let me try first to clarify, and then I'll try to answer your question, which is I think. So I mentioned monotonicity with two different meanings, two different uses.
Yeah.
So one is the definition of weak vective explanation. So the predicate itself is monotone, and we can use that information. That was the first time I mentioned monotonicity. Then the second time I mentioned monotonicity is monotonic classifiers. So you have a monotonic classifier if you increase one of the features, the prediction can only increase, and for that you need an order of the classes, for example. So that was the second time I mentioned. What you are saying is interesting, and it's a different setting than what we consider. So you are saying that I don't specify all the features, I specify some of the features, and then if I specify more features, something different happens. In our world, that cannot happen. Again, it's a very good question, so that's why I'm trying to answer it the best I can. In our world, it cannot happen because if you don't specify a feature, that means you can allow any value on the feature.
Okay.
So essentially, you are quantifying the feature universally. So what you need to do is you can specify a bunch. You need to specify all the features, or if you don't specify the features, then you are changing the problem, and you are saying, okay, what is the explanation, assuming that the feature is irrelevant or can take any value. Now that raises a number of other questions. Because of course, if you don't specify one of the features, then you should know that that feature is not relevant for the value, because otherwise you will be changing the value. So yeah, that would require again changing our definition of explanation. What we are requiring is that for us, a set of features is an explanation if the other features can take whatever the value they want to take, and that will not change the prediction.
Okay. Or you can think of assigning some default values.
Yeah, well, true, but yes, that's a very good. That essentially is it has to do with the problem that machine learning is usually extremely ill-defined. So unless when you get a data set, you don't have default values. For example, you don't even have the domains of the features. You don't even. So it's extremely problematic to formalize some of this, so that's why it's not been easy sometimes, because, for example, suppose you have a real valued feature. Okay, it takes values in the data set. It's 3.5, 2.8, and so on. Okay, can it take value 225? Unless someone tells us that, so that is specified, our reasoning methods need to be able to accept that. So yeah, it can be the fact that machine learning is often ill-defined is problematic when you are trying to reason formally about machine learning. And this is not just for explainability. This is also true for robustness.
Okay, thank you very much.
Thank you. Is there a last question? Or maybe we can thank again Joao Marques-Silva.
Thank you.